Okay, so here we're going to introduce you what are called phase portraits. And so a few videos ago, I would have considered this coupled linear differential equation system. And we went and solved it. But what does this actually mean? Like, what is that telling us? I know this is the rate of change of our x values related to x and y. The rate of change with regards to time of y is also related to x and y. But like slope fields, what happens when x equals -5 and y equals 5? So as we consider different coordinate points, we're going to get different rates of change for x and different rates of change for y. So let's actually take this and plug it in and let's see what we get. So dx dt, if we plug in -5, is equal to -5 plus 3 times 5 is 15. That is going to equal to +10. And dy dt, similarly, will be -5 minus 5 more will give me -10. And so this is a vector. So at the point -5, 5, I know that this is a vector of rates of change is going 10 in x, and then -10 in y. It's going in this direction here. And so every single point x and y can be shown as this vector. And so here is, like slope fields, here is the phase portrait. That's what this is called, the phase portrait. So if I look at 3, 5, at -5, 5, so -5, 5, which is roughly here, I know it's going to be over and down. So this vector is like 10, -10. And so it is going here, which is like 1 to -1 is the scalar multiple. So it has an angle of 45 going down, and it even shows the angle. And so with technology, it can be done that you can draw these phase portraits. Not all technology shows the arrows, but they're kind of nice when they do. So that's what's happening at the point -5, 5. It's going straight down. You can see that. So now when we consider our initial point that we did on the last time was 3, 5 when I did at t equals 0. If I go 3 and 5, that's roughly here. And so if I follow the arrows are taking me really up along here kind of thing. Oh, so here is an estimate of the solution curve for that we cover that with the initial value of 3, 5 at t equals 0. But as you can see, every point will have a very different solution curve. And the phase portrait can help see us. There's a lot of, that's very dynamic. There are a lot of moving parts. So here's an actual phase curve, the same one we just did. If I put on 3, 5, I can see that it goes here. And if I want to do all kinds of values, I could put one here and see the point, or here and see, or here, and you get all of these different kinds of, depending upon the initial points, you get all kinds of different interactions that occur. What you will notice, what's happening though, is they all, on this particular one, it has a certain look to it. And you'll see that it has this kind of certain, and there's an asymptote here, and an asymptote here, and we're going to talk more about that a little later on. But every of these points has a very different solution, and so it's very dynamic, and a lot of moving parts. And that's your introduction to phase portraits.